this video, we're going to look at equilibrium expressions and what the K value actually means. In class today, we looked at how we can make our equilibrium expression based on the balanced equation. So for our chemical reaction, A plus 2B giving us 2C plus 2D, our equilibrium expression would be K equals the concentration of C squared times concentration of D squared divided by concentration of A and the concentration of B squared. The exponents for these are coming from the coefficients in the balanced equation. Now, if we actually do an experiment and we measure the initial values of the concentration as 0.141 for A, 0.282 for B, and nothing for C and D, since we have reactants and no products, our reaction will take place. When this reaction eventually comes to equilibrium, we find that our concentration of A is 0.00167, 0.00334 for B, and the concentration of C and D is 0.279. In this reaction, we can see that the changes in concentration correlate to our coefficients. If the drop in concentration of A is negative 0.1395, then we should see a corresponding decrease in concentration of 0.279, which is double the value of 0.1395. And that's because of the 1:2 ratio on our balanced equation. We should also see a corresponding increase in the concentrations of C and D. Now C and D should be equal in their change because, again, they have equal coefficients. And if we look at the values, their change of an increase is the same as the decrease in B. Again, because of our 2:2 ratios. If we carry out another experiment, we see that the concentration of A and B begins as 0, and a concentration of C and D is going to start off as 17.5. In this case, we're starting with our products and going to run the reaction backwards until equilibrium is established. Again, this is possible because this is a reversible reaction, and both the forward and reverse reactions can take place. Our final concentrations are A's concentration will be 0.3916, B's concentration will be 0.7832, and C and D's concentration will drop to 16.7. And just as we saw before, these changes correspond to what we see stoichiometrically. Our decrease in C and D is correspondingly the same for an increase in concentration of B. The concentration change for A is actually half of those changes because A has a coefficient of 1 and should change by 1/2 of what the others did. If we look at these final concentrations and plug these values in to the equilibrium expression that we derive, the values when plugged in for experiment 1 would give us this equation, and when solved, we get 3.25 times 10 to the 5th. If we do the same with experiment 2, we will see that the solution is going to be 3.24 times 10 to the negative 5th. When we follow our significant digits, our variation here is not all that great. And because these may be actual experiments, there is going to be a little bit of fluctuation. So in a sense, our equilibrium constant is going to stay the same. No matter how we run the reaction, no matter what we start with, our final concentrations will end up being equal to the value of K. K tells us what the proportion of all of the elements at equilibrium will be. Any other situation, if these concentrations do not equal K, then it is not at equilibrium. The reaction will run until equilibrium is established, and the concentrations for all the compounds will equal the value for K at equilibrium. An example of this is our reaction that we saw in class, in the reaction of dinitrogen tetroxide reacting to form nitrogen dioxide. If we carry out a reaction and we begin with a concentration of 0.03265 and a concentration of 0 for our products, and we end with a concentration of 0.007184 for our reactant and a concentration of 0.5094 for our nitrogen dioxide, we can use these values to determine what the equilibrium value would be from the equilibrium expression. We simply plug in and say K is equal to the concentration of nitrogen dioxide squared divided by the concentration of dinitrogen tetroxide. Plugging our values in, we get a value for K of equaling 0.3612. Since this reaction was run at 100 degrees Celsius, any equilibrium established when dinitrogen tetroxide reacts to form nitrogen dioxide, those reactions' equilibrium constants will be 0.3612. So no matter what combination we begin with of either reactant or product, or a combination of both reactant and product, the reaction will run so that the equilibrium values will equal 0.3612 when plugged into the equilibrium expression. We can use this to our advantage. Say, for example, we have a reaction and we've measured the concentration at equilibrium of 0.1645. What's the concentration of nitrogen dioxide? Since we know what the equilibrium expression is, the only variable that we're missing is the nitrogen dioxide. So if we plug in the constant that we just determined, 0.3612, we plug in x squared for our nitrogen dioxide, because in our equilibrium expression, nitrogen dioxide is squared, divided by the concentration of dinitrogen tetroxide. If x is equal to our concentration of NO2, then we will get a concentration of 0.2438 moles per liter. So at equilibrium, if we have a concentration of 0.1645 for dinitrogen tetroxide, our concentration of nitrogen dioxide must be 0.2438, and that is defined by our equilibrium expression and the value for K. One more example. The production of ammonia is occurring in an equilibrium reaction. 1 mole of nitrogen gas and 3 moles of hydrogen gas will react to produce 2 moles of ammonia gas. But this reaction occurs and reaches an equilibrium. The equilibrium constant at 300 degrees Celsius is 4.34 times 10 to the negative third. That value then sets what ratios that we can have for any set of concentrations. So if we have concentrations of nitrogen and hydrogen of 0.365 each, what will the concentration of ammonia be? The equilibrium expression for this reaction is K equals ammonia concentration squared divided by nitrogen's concentration multiplied by hydrogen's concentration cubed. If we plug in our values given above, setting the value of ammonia's concentration equal to x, we get this equation. Simplify and isolate the x squared. We get x squared equals 7.70 times 10 to the negative fifth. Take the square root of both sides to simplify even further and get the value of x. And we get x is equaling the concentration of ammonia, and that concentration will be 0.00878. So our equilibrium expressions, again, define what the equilibrium conditions will be when a reaction reaches equilibrium. The K value determines what all of the reactants and products, what their ratio is. The only thing that's going to change the equilibrium value would be temperature. And that's why most of our reactions, when the equilibrium value is given to you, it is given to you at a specific temperature. If the equilibrium expression is known and the equilibrium constant is known, we can use that equation to determine unknown values at equilibrium.